Hello, everybody, and welcome to session 8 of the 13th Safety Gala virtual workshop. I'm delighted because we will have in this session great speakers and leading experts in the domain of safety. We will have Professor Chris Johnson and Professor Nancy Levinson and Mr. Eli. We will wait Mr. Eli a few minutes. He will join us in shortly. The main subject of this session is incident and accident investigation. It is something that every organization should be looking at if they are truly interested in safety. And we will start our talks with Professor Chris Johnson, who is also a Pro-Vice Chancellor of Engineering and Physical Sciences at Queen's University, Belfast. Over the last 20 plus years, he has authored more than 200 peer-reviewed publications, including one of the first textbooks on accident and incident reporting. He has held fellowships from NASA and the US Air Force and Navy. He is scientific advisor to the European Commission's Single European Sky Joint Undertaking Initiative, the future of air traffic management in Europe, and helped author guidelines on incident reporting for Eurocontrol and the European Railway Agency. He also helped the UK Department of Transport to develop the National Cybersecurity Strategy for Aviation. And in 2021, he's one of some 15 expert witnesses retaining to support the public inquiry into the Grenfell Tower fire, which has happened in 2017, I think, Chris, in London. So, Chris, if you can share your screen. I need to remind everybody the possibility to send your questions and answer at the appropriate field, the bottom right section of the screen. And we can start with Professor Johnson's presentation. So.
Okay, thanks for the introduction and welcome to Belfast virtually. I thought I'd talk about a bunch of projects that we've been running, both in Belfast and previously where I was based in Glasgow. And a lot of the work here is due to my students, not me. And we're trying to bring together the fields of safety and machine learning that are fundamentally incompatible, but that the rest of the world would like to bring together in lots of dangerous ways. So I'm going to just spend 1 or 2 slides on incident reporting. And when I say incident reporting, I'm probably talking about mishaps, both accidents and incidents, but my focus will shift in different contexts, and maybe people can pick me up on that later on. And then I'm going to look at 2 different areas for machine learning within the safety management cycle. The first is a kind of obvious one, which is the use of machine learning to identify and extract patterns from incidents. And it's kind of cool that Nancy's talking later on, because obviously I think one of the weaknesses of that is you tend to focus on large numbers of previous small consequence failures and not the myriad of successful events that resilience engineering has taught us to look at. But if we were more careful in how we collected data, maybe we could look at that too. In other words, use automated reasoning and automated learning systems to identify why something went right, but that's slightly harder. And I'm going to look at a second area, which is to look at what we can do to use accident and incident reporting to increase our confidence that machine learning is safe. Because right now, lots of the companies around the globe are struggling with this. So they would like to use, for example, autonomous driving platforms, and then one accident or one incident puts their product back 5 years. Okay, so what can we do to use incident and accident reporting to improve the safety of machine learning? Or put diagrammatically, the first thing I'm going to look at is machine learning applied to the organizational or operational feedback between implementation and risk assessment within the safety management cycle. And then the second thing I'm going to look at is machine learning within this gap between design and implementation. So can we insert machine learning to make our implementations more resilient, more tolerant of failure, for instance? So first thing, machine learning with incidents. How can we use machine learning to identify patterns in large bodies of incident-related information? The old manual systems, this is the US Army's field manual for incident reporting, used to try and improve consistency and coherence through forcing people into boxes. So personnel in the field, when they were categorizing accidents, had to follow the flow chart, and it, as I think people will talk about later on, it tends to focus your attention very often onto things like individual failure as a causal explanation. Second generation started to automate that, and again, human error always was probably one of the easiest areas to click. So the top of many menus was usually operator performance, and the bottom would be things like inadequate finance. This one's from European aviation industry. Then I kind of joined, and we were trying to look at things, different things that we could do. So what you see here, visualizations of more complex accidents. So the one on the top left is a 3D visualization of a timeline. And I know there are lots of problems with timelines, but there are things where, like, for example, Jonas mentioned that we're working on a Grenfell Tower, and that has hundreds of thousands of individual events involving different people involved in different flats and the emergency services and coordination across a massive scale to really understand why people lost their lives in that situation. And in that situation, you know, post-it notes and a whiteboard don't cut it. So that's the kind of thing that we're doing there. And of course, what you can do there is check for consistency automatically into the mishap investigation reports and so on. Again, the thing on the right and below are taking things like the cab recorders, in this case of an Amtrak train, and then generating automatically training material and driver simulations based on the incident reports. And again, it's trying to use automation to improve the output from accident incident reporting. That's just a kind of giving you a very rushed background to some of the things that have gone on recently in incident accident reporting. So now, machine learning, where does that fit? And I'm kind of trying to bust some of the myths about it. An awful lot of papers published in the area, but not very much value coming out of it. This is the US Food and Drugs Administration's manufacturer and device database, and hundreds of thousands of entries, of many of them of low consequence incidents, and there are huge problems in searching it. So for example, misspelling a manufacturer like Siemens, where it's very easy to misspell it, will lead to omissions when you issue subsequent search terms. And so data consistency is problematic. Many healthcare professionals who might want to look for similar instances to the one that they're concerned about lack the database skills to really be able to form search terms in traditional databases and so on. So we spent a bit of time trying to use machine learning to automatically partition the data sets of incidents. This is the output from a kind of a Spring tensor model. This is trying to visualize it, because the problem there again is that the people that want to use the results of the machine learning don't understand the algorithms. And what you see here is a database of railway signals passed at danger in the UK. And I'm coming here not to kind of promote this, but to explain to you what the limitations of this are. So for example, when we first started to analyze this data set, we got absolute junk out of it from the machine learning algorithms. The kind of thing that we were getting back were, and there was a certain element of humor here, but the general point is true. The kind of things we found from first level of analysis from the machine learning is that the name of the driver most likely to have a signal passed at danger on the railway is called Dave. And that the most frequent position in which an incident is likely to occur is also a position where there is the most railway traffic. These were not things that we needed machine learning to tell us about. What we did discover that we didn't realize before is that the highest number of railway suicides occurred around areas of economic deprivation with certain other geographical features and certain other sites of railway service that enabled us to locate where we should put fences up to keep people, potential suicides, effectively apart from the railways. But in other words, when you apply machine learning algorithms to incident data, you often get spurious correlations, like the driver called Dave. you're learning from past failures, but what's happening now is a lot of the machine learning algorithms, for example, that we've been applying to European aviation just don't apply because nothing in our data set prepares us for COVID. So we could take all the machine learning stuff that we did for the last 2 years and put it in the bin, right? Because you're learning from past failures, not future accidents, if you like. And the third point is something that I'm sure Nancy will raise, is that you're learning what causes previous mishaps, not what prevents potential mishaps. In other words, you're learning from the incidents. And these are all things, these are all research questions that many of the papers that are being published in this area have ignored. And there's lots of papers out there that just, you know, machine learning looking for another problem. But these are 3 research questions that I think people here should be looking at. And also, if companies are sold products in this area, these are the things they should be concerned about. Okay, check time. Not too bad, halfway. Right, so yeah, let's look at the second thing, which is how can incident reporting and accident reporting and safety management techniques be used to increase our confidence in machine learning when it's put into safety critical systems? Well, first thing to say is that traditional software standards are not applicable. So Tesla, for instance, and many of and Waymo, for instance, providing autonomous vehicles, the applicable functional safety standard that you may be familiar with is something called 26262, and it's very, very difficult to apply that to machine learning, because machine learning is about the analysis of data, the extraction of the data, the development of test cases, and then the generalization of those test cases. You know, does your test case prepare your system adequately for the environment? Whereas 61508 and 26262 are based around traditional life cycles of software that go from requirements through specification and so on. In consequence, when you look at the guidance for 61508, you'll see things like artificial intelligence for fault correction not recommended at any integrity level. However, at the same time, everyone around me is saying, can we put machine learning into safety critical systems? And this is really, really important, because, you know, UK government is about to invest in this area. The European Commission is investing in this area, and COVID has actually exacerbated it, because with reduced traffic, it gives us an opportunity, for example, in air traffic management, to begin experimenting with machine learning as a way of reducing the cost base. In other words, fewer flights mean fewer controllers, mean we need some other ways to continue to operate our air traffic systems. And machine learning is seen as a potential solution to that. Another area you might be surprised is that people are looking to machine learning to not just improve flow in terms of air traffic management, like we saw in the previous slide, but they're looking to improve safety in the nuclear industry through the application of machine learning. You know, 5 years ago, I would have said there's zero chance of seeing this. I put in some of the MIT work as well here in the use of machine learning in the nuclear industry. If this is going to be successful, then we have a huge amount of work ahead of us. And if there's nothing else you remember from today, from my presentation, then there is a fantastic paper between Harvard and Microsoft called Failure Modes in Machine Learning. It's quite old, and there's better papers now, but this is the one that started it all. And it goes into the bugs, if you like, the wrinkles, the algorithmic flaws that occur in most machine learning algorithms. And the second half of the paper, which I haven't got time to go into, looks at cyber attacks on machine learning algorithms. And it's important because the cyber attack part is based on evidence, and that evidence is available through GitHub. So if you go to GitHub, you can see a repository, Microsoft, Apple, NVIDIA. You know, there's about 30 or 40 large companies that have put in information about attacks that they've experienced on their machine learning algorithms. And seeing in the background of this talk, which I'm not going to illustrate it with, is basically military examples that we're looking at here, but I'll use civil examples in this talk. So how do you convince people that machine learning is safe enough? Well, the most obvious thing at the moment is exhaustive testing, which of course Nancy, Jonas, and others have spent their lives saying is not sufficient in software. So how can we be confident to basically throw out everything that we've learned and say, yeah, exhaustive testing is enough? Well, I don't think we can. And to be honest, we've been in that cycle. We've been in the cycle that we have gone through many, many times. Even in my career, we've gone through it, where people try it, fail, and then re-examine things. So this is the fly, fix, fly approach. many of the autonomous vehicle programs have suffered incidents and accidents. And if you go look out on the web, you'll find that many of the companies that I mentioned earlier on are now recruiting engineers who have experience in 26262 and 61508 because they're being forced by the regulator to look more at the software quality, including the machine learning algorithms. But the processes in those standards, functional safety standards, are insufficient for machine learning. So another thing that you see around the world, both the United States, Europe, and Singapore, I think, is excellent in this, is the sandpit idea, where basically you reduce the regulatory burden on companies. And so you can introduce machine learning with less liability. And that creates things like waivers to the Code of Federal Regulation. You see that in the use of drones within the United States and national airspace. In the UK, we have areas where you're allowed to use autonomous vehicles and interact with public to a degree that you wouldn't be outside of those zones. And the problem there again is that the incident information is only coming out of potential situations where the public is put at risk. Whatever we say, we are seeing a large and growing number of incidents. So if you look at the NTSB websites or the UK Civil Aviation websites for drone-related mishaps, there is a sufficient database there now to begin to see patterns of failure within these applications, even though many of them are not being thrown fully autonomously. So what people tend to do in these sandpits is restrict the environment. So you try and use your information about previous incidents and then allow machine learning in environments where those incidents can't occur. So we've seen incidents where pedestrians have caused accidents with machine learning in autonomous vehicles, and so therefore you exclude pedestrians from the area that your autonomous vehicle is working in, but thereby you also reduce the benefits of the system. Another way that we could do it is through robust training sets. In other words, we use incident information to identify the training sets that we then expose our system to. So we demonstrate safety not through exposure in the environment, but through putting the algorithms, if you like, into situations that are specifically designed to test them. So both Waymo and Uber have absolutely massive libraries. So each of those 20 billion miles that you saw previously referenced in the Waymo testing has logs associated with it. And there's a formal process where incidents are examined within those logs and then carried through into a library of test sets. So in effect, the incident information that's gathered from exposure to the real environment is then used to inform the future testing of machine learning algorithms. But I think there's a huge opportunity here for systems engineers to engage more formally in the processes that are used to increase confidence in machine learning. It's not systematic, and it's ignoring things that people in this audience, I think, have learned over many, many years. There's too much focus on the mathematics of the algorithms and not enough on treating safety as a subject in its own right. So I put a slide together here again, just pointing out not the benefits of machine learning in safety critical systems, but the real problems that arise from machine learning here. So again, same point. The training sets, if we introduce incident-related information, are often based on past failures and not future hazards. So for example, I showed you a picture of the Sentosa coach in Singapore. One of the problems for the coach in Singapore is that the algorithms, the machine learning algorithms, have turned out to be too conservative. So when you come up to a roundabout, it is so nervous about conflict with other drivers that it waits so long that the human passengers then try to get off the bus, because they're not prepared to wait for the algorithm to be sufficiently convinced that it's safe enough. Now, that's not a behavior that you see normally under any other circumstance. It's one of these emergent properties, if you like, that, again, systems engineers are totally familiar with, but in the machine learning context, people are like, oh, never expected that. Again, the idea of resilience engineering and tying up all those arguments about when things go right, those aren't the things necessarily that carry forward into the databases that the autonomous vehicle companies are gathering. You know, it would be really cool to see what is the best possible scenario for an autonomous vehicle in certain contexts and then reinforce those. I think that is being done now, but it's taken a long time to get to that place. And then the third point, which again, I haven't got enough time to go into, is that military organizations around the world and intelligence organizations are looking specifically at ways to defeat machine learning algorithms. So what does it take to fool a machine learning algorithm that it is not seeing an image of an F-35, for example? So the cyber role is something that Microsoft is stressing, and that paper that I mentioned between Microsoft machine learning department and Harvard ethics group on the use of machine learning in safety related applications is absolutely essential if you think that this stuff wouldn't go on, and how would you fool a machine learning algorithm in a cyber context? So there we go, that's me. I introduced incident reporting. I talked about kind of the conventional big hype about machine learning and incident reporting, and then pointed to 3 of the problems that we've observed from the application of it. And then I went on to look at another thing which is less spoken about, but how can we use safety engineering and incident reporting to increase our confidence in machine learning and safety applications? And again, I tried to say, Chris is not trying to hype this up as a big area. It's going to happen whether we like it or not. As I mentioned before, there will be sections of UK airspace in the next couple of years that will be exposed to machine learning algorithms. And it's our job, I think, to use our systems engineering experience built up over at least my working lifetime to make sure that we don't fix, fly, and risk the lives of the public, and put back the field of safety engineering and machine learning a decade through inadequate communication between the communities. That's it. Thank you.
Thank you very much, Professor Johnson. That was a very interesting presentation. Thank you for enlightening us about the machine learning and artificial intelligence and how we can use it in safety and especially in incident investigation, and to what extent we can ensure its proper operation. So we can be skeptical a little bit. It is a new domain that needs to be matured, I think, significantly. So it is up to us to evolve it furthermore and see where it will go. So thank you again. I need to remind everybody that if they have any questions, they can write them down on the proper text section in the bottom right part of the screen. So next presenter is Eli Abu Zadeh. Eli is, let me find my notes. Eli is working for Consolidated Contracting Engineering and Procurement, holding a position of Regional Health Safety Executive Manager for Kazakhstan. All right, so Eli, thank you very much, and we are looking forward for your presentation.
Hello, good evening. Thank you for hosting us. Thank you for Management Force and for all my colleagues. Nice meeting you all. Very nice presentation, Chris. We really enjoyed it. As you had said, I've been working in the HSE industry for more than 12 years, mainly within the EPC scope of work on mega projects. Currently, I'm in charge of Kazakhstan and the CIS region under the leadership of the Regional Managing Director of CCEP. Today, I would like to give a presentation about the establishment of HSE culture with hands-on experience and insights from the tallest tower in Central Asia. Currently, I have one of the mega projects under CCEP, which is around 1.8 billion US dollars contract value, with the peak manpower of more than 10,000 active on site, building the highest tower within Central Asia as part of a 500,000 square meter area development. So we will be providing some insights based on this project. Just a second to connect you to my desktop. My apologies for this. Are you able to see my desktop?
The Explorer?
Hello? Excuse me, can you
Yes.
see the desktop?
Yes, I can see the Explorer.
Ah, you cannot see the presentation?
Nancy, could you please, because we have this technical difficulty, could you please begin your presentation, and Ellie will continue afterwards? For some reason, I cannot hear you, Nancy. Maybe, I do not know.
Yeah. Sorry, I was muted. So I'm going to talk about how we can learn more from accidents and incidents and events in general. I've been on a lot of accident investigations, and the major ones seem to do a pretty good job, but still not great. And the minor things, 99% of the accidents just are never investigated very well. And so the question I'd like to talk about is, why aren't we learning enough from accidents, and how might we learn more? And there's certain common problems in accident analysis. Root cause seduction, oversimplification of causes, hindsight bias, a focus on blame, and a narrow view of human error. So I'm going to talk about each of these a little bit. So let's start with root cause seduction. We love to believe that there is a root cause, and usually management doesn't want to hear about more than one, two maximum, and that's all they want. And the reason we like this is because it gives us an illusion of control. And if we only have one or two things to fix, then it looks like we've easily solved the problem. They usually focus on operative error or technical failures. They ignore the systemic and management factors. And this leads to a sophisticated whack-a-mole game where we fix the symptoms, but not the process that leads to those symptoms. And we end up in continual firefighting mode. We're continually having the same accident over and over again. The symptoms are different, but it's really the same accident. Part of the problem is, and related, is the oversimplification of causes. In every accident I've ever seen that we actually looked at in any depth, there's always operator error and flawed management decision making, and flaws in the physical design of the equipment, and safety culture problems, and regulatory deficiencies, and so on. And so unless we look at all of these things, we limit the learning that we can do. We want simple answers to complex problems, questions, but that doesn't really provide us with any progress over the long term. A second problem is the limitations in our accident causality models. The accident causality models identify how we learn from and try to prevent accidents. It's how we believe what is the cause of accidents? Why do accidents occur? And the most prevalent one for the last couple of hundred years has been a linear chain of events model, where event one causes event two which leads to event 3, which leads to event 4, which leads to event 5. It's very linear. It's 90 years ago, this was called the domino model. Each domino following causes the next one. A newer incarnation is Reason's Swiss cheese model, but it's no different than the domino model. I don't know why people think this is different, just drawn in a sexier way with the Swiss cheese slices, but it's the exact same thing. It is even more limited because it really makes everything the human operator problem. Everything is humans on this thing. Well, he's a psychologist, it's not too surprising, but unsafe acts lead to the loss of the mishap. But you know, the wings could fall off the airplane and we'd still blame the pilot in this model. So what are some of the limitations of this model of chain of failure events? Well, and mostly these are all failures of some kind. You'll see it calls them failures, and in the same thing, these are all failure events. So what are limitations? Well, we're assuming that all of these events are independent, that everything is related, is unrelated, and therefore, and we don't have any circular feedback loops or anything more complex. We end up blaming the human operator or a physical failure in the chain, almost always. We can't handle complex human behavior. We can't handle software, system design and requirements flaws, systemic factors, design flaws, organizational social factors, culture, accidents involving non-failures, because these aren't events. They're not failures. They're conditions. There are other things in the whole safety management system that are flawed. And we can't handle interactions among the causal factors. So everything becomes very simple and very simplistic. And to go forward, we're going to need new, more powerful models of accident causation. We have the STAMP model. It's based on systems theory rather than reliability theory, but there's other possibilities that people could use, but we're going to have to do better than we're doing now. Another problem is hindsight bias. Before an accident, everything looks very complex, and then something happens, and afterwards it's very easy to see what went wrong. And you see this all the time, this hindsight bias. After the fact, it's simple, and we say, well, why didn't the operator notice this? We see it. And you see this in every accident report. Some accident reports, I see it multiple times on every page, but it's everywhere, especially in the causation section. And so what you see is should have, words like they should have, they could have, if they would only have. So for example, the failure of the flight crew to discontinue the approach into Cali, Colombia, despite numerous clues alerting them of the inadvisability of continuing the approach. Those cues were only relevant and only noticeable after the accident. At the time, they weren't noticeable. The board operator should have noticed the rising fluid levels in the tank. Well, there was no way. It wasn't on the control panel. There was no way they could have seen that the fluid, the flow monitor showed no flow. They had turned off all the intake pipes. Everything supposedly should not have happened. There was no way they could have noticed it. So after an accident, it's easy to see where people went wrong, what they should have done or avoided, and to see what piece of information turned out to be critical. When they were bombarded with all kinds of pieces of information at the time, it's almost impossible. You psychologists have shown it's almost impossible for humans to go back and understand how the world looked to someone not having knowledge of the outcome. We've got all the connections in our mind and our brain. And it's hard for us to see what's so obvious to us now after the fact. So in order to learn, we need to stop identifying what humans did wrong. That provides no way forward and no important information. we've got to start from the premise people do not come to work or people to kill someone. They don't get up in the morning and say, oh, good, I'm going to kill myself or someone else today. Or designers don't say, I'm going to work and build something that's totally unsafe. We need to identify why it made sense for people to do what they did. Then we can solve the problem. This is something Sidney Dekker has talked a lot about. Blame, another problem is a focus on blame. The goal of the courts is to establish blame. And when you put blame into an accident investigation, people stop reporting errors, they hide information, you don't learn anything. Learning stops as soon as you have blame. The goal of engineering is not to find blame. That's not our goal. Our goal is to understand why accidents occur in order to prevent them. We can leave blame to the courts and let them worry about that. We shouldn't be wasting our time on it. So there's two really approaches to accident investigation. The accusatory approach, which is what almost everyone does. Who did it? Who was wrong? And the explanatory approach to accident investigation says what. And so for accusatory, we look at who and then we try and look at why. For explanatory, we just look at what happened and why it happened. And we take blame out of the equation and we learn so much more that way. Finally, do operators really cause most accidents? We've all heard the statistics, and you find out all the time, everybody's 70 to 90% of accidents are caused by operators. Is that really true? Well, the traditional view makes this assumption that operator is the cause of most accidents. The accident reports always end up saying that. So we should do something about the operator involved, fire them, retrain them, whatever, or do something about operators in general. So we'll marginalize them by putting in more automation between them and the system, which only makes things worse and more likely to have an accident, or we rigidify their work by creating more rules and procedures that they can't follow and won't follow. This is from one of the same accident reports. This is the Cali Columbia crash with American Airlines. The failure of the flight crew, this was one of the 4 causes. It was all flight crew causes, but this is my favorite one. The failure of the flight crew to revert to basic radio navigation at the time when this is flight management system, the software assisted navigation became confusing and demanded an excessive workload in a critical phase of flight. Look what they're doing there. They're blaming the flight crew for the software being confusing and for demanding too high a workload. That's not the flight crew's fault, but the flight crew still got blamed for it. It's absurd, but you find this in I find this in every accident report, and I read hundreds of accident reports because I do a lot in accident investigation now. Fumbling for his recline button had unwittingly instigate the disaster. This is the systems view. A newer view of human error is that human error is a symptom, it's not a cause. All behavior is affected by the context or the system in which it occurs. And we're creating contexts and systems where, first of all, the role of is changing. They're supervising rather than directly controlling, which changes a lot of the important factors in accidents. The systems are so complex, they're stretching the limits of comprehensibility. The engineers can't understand them all and all the implications of these systems, let alone the operators. And we are basically designing systems in which operator error is inevitable. And then we blame the accidents on the operators rather than the designers. So to do something about error, human error, we have to look at the system in which people work. The bottom line is that human error is a symptom of a system that needs to be redesigned. So here's my conclusion. I'm finishing a little early so that we'll still have time, although we lost some time. The model used in accident or incident investigation analysis, loss analysis, determines what we look for, how we go about looking for facts, and what facts we see as relevant. The linear chain of events model, which everyone uses, promotes looking for something that broke or went wrong in this proximal sequence of events prior to the accident. We choose some kind of stopping point arbitrarily in this thing, and we call that the root cause. It's totally arbitrary. You could call anything the root cause. And unless we look further at accidents, unless we look beyond the chain of events and the events that occurred, and we look at why those events occurred, we limit our learning, and we almost guarantee that future accidents are going to be related to the exact same factors that have happened in the past, and we don't improve. The goal should be to learn how to improve the safety controls, the safety management structure, and not to find someone or something to blame. I just want to mention we have a workshop on this, June 14th to the 26th. Last year we had over 2,300 people registered from 73 countries. There, if you want information, it's at this website, psascripts.mit.edu. And if you want more information, also there's a book, you get a free download of this book from the MIT Press. Look in, just Google it, and you'll get the free version comes up first. We have an Sdpa Handbook, which is now had, which is our analysis method, hazard analysis. We've now had over 100,000 downloads in the last 2.5 years. It's been up on the web. There are Japanese, Chinese, and Korean versions have been translated by engineers. And a CAST handbook, which is how to learn more from accidents and incidents, which is the topic of this. That's there. It's newer. It's been translated into Korean recently. And you can find more information there. Finished.
Thank you very much, Nancy. Let me say a few words first before I move to Eli. Dr. Nancy Levison is a professor at MIT.
Oh.
And I didn't introduce you because I know you quite well. So I thought everybody knows you. So let me do the formal things first before I move to Eli. Nancy is a professor at Aeronautics and Astronautics Department at MIT, and is also the person who introduced the STAMP accident causation model in 2004. So thank you very much, Nancy, for your presentation, and we can move to Eli Abdul-Jader, who can continue. Can you upload your slides now? Is it possible?
Yes, we tried it. Oh. I'm not sure why we are having all of this. Again, stop.
We lost it. We're seeing it.
Hello. Again, we apologize for this technical error. As we said, we're going to address briefly about the establishment of HSC culture on mega EPC projects and some highlights from the tallest tower in Central Asia. This is our outline. We'll be discussing about the synopsis of risks and challenges, the economics and VAR with the costs and effects, the tools for performance tuning and HSC homologation, and the drive towards a zero tolerance culture. As we all know, the EPC industry, especially the construction, is one of the highest risks imposing industries on the aspects of HSE and on commercial developments. The high risks and severity rates of serious incidents encounter serious injuries, fatal accidents, workforce and internal interfaces and exposures, especially on health and well-being of our people, and the impact on the ecology. The challenges is that based on the latest studies of the market, the demand for energy will be increasing more than 50% by 2030 due to the economic progress and the development of the population, meaning during bidding and estimation phases, projects will be put on fast-track projects, on fast-track schedules, to complete the requirements in a short term and concise timeframes. This induces additional risks on human perception and behavior, especially during the execution of works, where people tend to take shortcuts to safety. As well, the construction industry has a very dynamic risk, where every day is a new challenge. Risks include many variables that are imposed on daily basis, some of which are the resistance to change from workforce, where people tend to say, like, we have been doing it all our life like this, however, nothing happened to us. This is the role of HSC experts to mitigate this risk and to induce an aware HSC culture that will change this perception of our workforce. Heavy works and simultaneous operations. It is very common within mega EPC projects to have mega heavy works, mega activities, and simultaneous operations. The challenge is to mitigate and to lower the impact of these activities by segregating simultaneous operations, which we will go throughout the presentation. As well, foreseen challenges within the EPC industry is the mass number of workforce and the immense spread of areas, which puts a burden on contractors to have competent and highly committed WRPs, work responsible persons and supervisors, to manage their crews in a way not to have them loose and commuting within these high spread areas, which will affect their health and safety and will affect their productivity from another hand. Workforce maneuvering, accommodation, massing, and committees. Apart from the headaches and the challenges and risks of the physical execution of the works, you have workforce management. And in CCEP, we have been working heavily hand in hand with the local communities and with the establishing industrial relation committees that would care for the workforce, will listen to their griefs, will understand their possession and what are their their demands and needs to have a healthy stay during their work within our camps. As well as the global pandemic is still been hitting the world, COVID-19 prevention and controls is one of the greatest challenges, especially when you have mega number of people. You have interfaces with external controlling bodies, whether the client, consultant, authorities, certifying bodies, NGOs, surrounding communities, especially when you are operating such a mega project in the heart of a city. The environmental factors mainly are the weather challenges, where a lot of our colleagues we've seen during management force, Gala safety, they operate in the Gulf. They have the similar challenges we have, but on the other side of the thermometer. In beautiful Kazakhstan, we have extreme low temperatures, similar to the Gulf, which they experience high temperature. As well, having mega number of people active on site, access control and undesired acts are very common challenges. And the challenge is to develop site-specific emergency response plannings, including social media mitigation, because anything cannot be hid anymore. Nothing can be hid throughout social media and electronic platforms. The emergency response plan is to mitigate unauthorized entries and possible undesired actions. Economics and VARs. This is the cost of an accident. The cost of an accident is the typical iceberg effect that we know, which induces increased costs on the indirects more than the directs, which is characterized mainly by loss of productivity, lost time and idle resources as a result of stopping down operations and site following a serious accident or an injury, slippage from the working schedule, investigation and corrective action time and implementation, the time exerted to have to raise the competency of our workforce and to compensate for the damages occurred in terms of property damage and workforce morale. I mean, workforce morale is one of the very important aspects that is being studied now worldwide. This is part of human perception and behavior. In many cases, in serious injuries, big traumas occur to workforce, which makes them afraid or untrusting the workplace to continue their works. Apart from having the diverse publicity, like as we said, internet has no mercy. News reaches the world before sometimes it reaches us. On a simple study we conducted one time for the cost of an accident, it shows here like 84% of the cost encountered was covered by the EPC contractor, where the insured cost was only 16%. So unshared and unbudgeted risks induce commercial burdens on all EPC contractors. This is the old model of cost of an accident. Although I have relatively different views, especially in terms of the costs, and in this era, when we say costs, it is mainly the man hours and the time invested into ensuring the continuous development of the management systems and the procedures, apart from the direct costs might included to automate the business process, the recording, and the trend analysis. I mean, people say that HSE might be expensive at the beginning, especially small contractors, but they never tried having an accident, which encounters huge risks and costs on their operations. The value at risk. This is from a commercial development perspective, when contractors or investors or developers tend to go and do investments, while the risk of having low HSE performance is one of the major causal factors that contribute to loss of investment. And loss of investment comes in an intangible manner and in a way that will impose a lot of resources to be implemented to rectify the issue, especially in terms of having idle sites, which increases the overhead on the contractor and the developer who is investing, and decreases the productivity rates, apart from the increase in insurance premiums and access to financial fundings from banks, from authorities, due to low HSE performance. Reputation affecting future investments, projects, and attraction of qualified workforce. As we said, social media has no mercy on anyone, and news are spread very fast. And as much as a person would be needy, they will not rather put themselves in death traps with contractors or clients that are showing low performance of HSE. As well, it puts the developer in critical industry stand and classifications, especially in terms of the certification process of their management systems, and in terms of bid management and pre-qualification for other projects. The resources, as we said, are tremendous in terms of training, in terms of direct costs and investments in certification of management systems, and apart from the indirects that we discussed previously. In our views, utilizing the HSE performance indicators and the stand of a contractor aids into further business development, where clients are very highly receptive to safe clients, because nobody is willing in the world to record a fatality or an incident on their records or names or reputation. As the managing director of British Petroleum once said, I quoted from him, "Prevention is not only better but cheaper than cure. Profits and safety are not in competition. On the contrary, safety at work is good business, and it is a good investment."
Just to inform you that we have 3 more minutes.
Excuse me? Hello?
Yes, just to inform you that we have 3 more minutes.
All right, I will go through very quickly into the tools. Tools to identify, to have a management system certified and homologated by a certifying body. The emphasis on automated tools such as softwares, such as the risk analysis and risk management softwares. These are snapshots of some softwares that are being utilized. This will enhance the recording of the contractor, that will allow for better analysis of the KPIs. I would rather go into the pictorial rather than the talking of this slide. This is driving HSE culture and insights from the tallest tower in Central Asia. Indeed, it is a challenging project. Management leadership and commitment is very important. We put in place a Save a Life program that is signed and sponsored by the regional managing director of CCEP, authorizing each and every worker to stop unsafe works. And these cards were distributed to our workforce, allowing and empowering them to stop any unsafe activities. This is a small highlight on the performance of the safety observation card system that we installed, that we are implementing in CCEP. It shows a breakdown and the number of reported cases. Reporting is the main tool towards establishing a high safety culture. These are some pictorials from the on-the-job trainings. Innovation has been done in terms of providing trainings to overcome the language barrier. Rather than taking people out from the site and putting them in training centers, we shifted and reversed the process. We have on-job trainings ongoing on different aspects of the works. Workforce committees and engagement, establishment of industrial relation committees that will bridge the link between supervision, management, and the workforce. Recognition of the performance of our workforce is one of the key factors as well. We've been assigning HSE ambassadors on zones where the winners and who are performing well, we have their photos shared along all the site and among all our people. Introduction of the wellness program. This is a program that I will highlight. It is targeted for people that have high BMI. CCEP has been deploying a risk assessment strategy to screen our workforce and to conduct non-invasive tests to evaluate their health status, and further to ensure their sustainable health and awareness. Sports and tournaments, dietitians have been deployed on site, apart from the health promotion campaigns to alter their perception and improve their way of living. At the end, I would like to conclude that HSE is not a priority, rather a value. because priorities tend to change based on circumstances and stance, while values are continuous, perpetual beliefs that will not end based on any circumstance. Thank you for participating. Stay safe and healthy.
All right. Thank you very much for your presentation, and we can have some answers to specific questions that were sent to us. One question, some of you, Nancy and Chris, already answered some of them in the chat. So let's briefly state them. My friend Deutschev, with whom we were in Paderborn, Germany, asked Professor Leveson why instead of accident investigation, not use the term loss investigation. And if you say a few words about this, Nancy, we will appreciate it to everybody.
Which question was this? I'm sorry.
It's about the question about why we use the word accident and not loss.
Oh yeah, we're not using it. We're trying to get away from it. We're starting to talk about losses, and all of our methods now work on general losses, including quality, including serviceability for John Deere tractors, farm equipment. We've been using the methods on that. We are not talking about, and diagnosability. We're not talking about losses, only safety. Any loss of reputation to the company. Any loss may be important, and it all works the same with STAMP and with our tools.
Thank you very much. Mr. Panopoulos asked Chris on the issue that some countries are not technologically advanced, so why they can use in order to utilize machine learning and other AI technologies to enhance their safety. So there was an answer there. If you can elaborate a little bit, Chris, that would be great.
Yeah, I would say that most of my students come from countries that would classify themselves as not being technologically advanced. I have lots of students from Africa, for example. And, you know, I think often their governments are keen to support what they're doing in the idea that they will go back and transfer some of those ideas back into their own industries. And I think there's fantastic opportunities there, because you can introduce, rather than going back and repeating all of the steps that we've taken to get to here, we can begin to look at things like machine learning algorithms and conversational reasoning tools that other people have used to handle large incident databases. You know, without the legacy that we've had to go through of relational databases and stuff. You know, because, for example, clinicians are expecting this of their applications that they deal with in healthcare. They're not expecting to go and use, you know, Excel-style spreadsheets that most of the rest of us grew up with. I think I put in the chat, which is that the very easy way to get things going quickly any part of the world right now is computing science. Faculties and schools are desperate for machine learning projects for their students. And, you know, just go talk to universities, at least in terms of the European spectrum that I know well. There is no country in Europe, and I've been to every single member state doing safety and security talks in the last 5 years pre-COVID, which does not have a resource that needs help and employment in terms of projects, because it's been an explosion of students interested in machine learning, far more than any that would ever be interested in safety. So fantastic opportunities. And then the last thing I would say is the Horizon Europe program has a large amount of money in areas in the application of machine learning that I think are downright dangerous. And without engagement with safety professionals, this will all go horribly wrong at some point in the future. So plenty of opportunities there. Even if you're not in a full member state, the affiliated state status enables you to join in projects either at cost or with funding from the European Commission. So lots and lots of opportunities without having to spend large amounts of money and to leverage the existing resources that are there.
Thank you, Chris. There are also the issue on data sets. Plenty of students, at least in my department, are seeking for data sets to train their algorithms, etc. So this is one issue. But you provided some information about the GitHub where they can find some data, and also the Internet of Things, which is emerging, where everything will disseminate data on its status, can help the problem of gathering data to train the algorithms. So, and that brings me to another question by Mr. Zeleskidis, who asked Chris if we can use simulation to train artificial intelligence algorithms. And if you can elaborate a little bit on this, Chris.
Yeah, it's a very, very hot area. People have learned the lesson that trying to dump a machine learning algorithm into the environment and do exhaustive testing is a quick way to end up with a lawsuit. And so this idea, people often use the phrase digital twins. So building, sometimes, you know, they're linked to things called adversarial machine learning algorithms that learn from simulated environments. And yeah, huge potential in this, but the problems that we all know about in safety engineering with simulations in the past don't go away. So how do you gain confidence that your simulation or your digital twin is correct? How do you cope with emergent behaviors? How do you cope with the representation of human behavior? How do you cope with the massive explosion of potential interactions where you've got multiple people or agents, if you call them, you know, going back 5 years? How do you deal with all that stuff? So it is a huge potential. It's a really easy area to get money now. It's, you know, if you want to fund a research program, talk to any of the large multinational companies at the interface, not necessarily between safety, but in the interface between operational research, simulation and machine learning, because ultimately safety is only one part of the larger economic situation that companies find themselves in, and they are already using these algorithms to inform decision making, including the operations departments of major airlines. So I think that really chimes with the last speaker, and it, you know, what I'm trying to promote is that the generation of students I'm teaching here, you know, I carry a baggage of having grown up in the, you know, from sort of 1980s onwards, and everything I see in terms of safety culture and safety organization is influenced by having grown up in an environment where, you know, Windows looks like a step forward, but that's not the case for the students that I'm teaching now. And I think that many of the methods in safety engineering have looked at those problems and solved those problems. And I'm seeing the same problem set arising with machine learning now that our students think is totally new. And all the stuff I said about simulation and digital twins, that they've not read the papers or heard the things that we've all experienced. So I think there's real importance for the generations to meet in this area. Otherwise, I think we'll go through what we went through in the 80s and 90s, which is pushing too far, you know, the kind of inevitability of accidents through progress and the para work and all that. And Sagan is on the doorstep because we're pushing machine learning algorithms too far into safety related applications, and we need more safety engineers to engage with it, and maybe less people who are only motivated by algorithmics.
Chris, questions from Mr. Panopoulos to Professor Nasser Levinson. Very, very interesting question. How to convince people to cooperate and help with accident investigation and root cause analysis, and at the same time to assure them that the cooperation process will not be included in the documents for the court hearings. So, Nancy, you are muted. If you can unmute your microphone.
This is a very long answer. It takes an hour to explain how you do this, but you can, and we've done it. It's related to the whole concept of just culture. You have to change the culture in the company. You have to gain trust from people, and you have to include them in the accident investigation analysis. So if you include the workers, some of them may have been injured in this. You get, and you train people to do this kind of non-blame type of accident investigation. It works, and it can be done, and we've done it. I have a method called CAST, which also helps. I forgot to mention it, but it's up on our website, and there was on one of the slides, or just write me and I'll send you it. But there are steps you can take to go through this whole thing that takes the blame out of it. And CAST just doesn't have blame in it. It looks instead at these kinds of other factors. And what you find is it forces you to look at the contribution of everyone and everything to the accident. Usually everyone contributed. As I said, there's all those factors. And once you get all the factors contributing, it's hard to just blame the operator. You know, I noticed in one of the presentations in Ellie's presentation, there was this thing about zero tolerance. That's a giveaway. You're telling the operators and the workers you're not going to tolerate any errors on their part, and that they're responsible for accidents. So things like that change, actually work against being able to do this kind of better investigation and being able to improve safety, in my opinion. So now we can have a good argument, debate.
Thank you, Nancy. And a question from Mr. Panopoulos to Ellie. How likely a mega project in rush and economically tight can use the benefits from Nancy's methods and what Chris described about artificial intelligence algorithms? What factors should be considered in these types of projects? Geographical client policies, contractor policies, financing, funding. I mean, how all these new ideas can be implemented in mega projects?
Yes, in terms of mega projects, I agree with all the ideas. When we were referring to zero tolerance, I mean, like, as a system built in, we will not tolerate any tolerance to possible HSE violations. So utilizing business intelligence, artificial intelligence, and automated business tools such as softwares that will aid and assist into reporting and identifying trends that will identify the gaps and possible opportunities for improvement are very essential. And I fully agree with Chris, and it's a very good idea that will create an additional layer to the Swiss cheese model that we've been implementing in an IT-aware and intelligent manner. In terms of how to apply it in terms of clients and financial institutes, as I said, if we follow Nancy's strategy and mechanism for handling investigations, corrective actions, and establishing this newly aware HSE culture, this will induce better performance on the contractors and will allow them to have better business development in the future and possibly access to financial funds.
All right. Thank you very much, Eli. So one question for Professor Levinson from Mrs. Haralambidou is about the utilization of probabilities.
Well, probabilities don't work. I mean, they're all made up. I mean, I can't tell you. I have looked at hundreds of accident reports, and everyone had a probabilistic risk assessment that said that the accident couldn't happen, and it happened. So, I mean, they've done 2 scientific studies to try and figure out whether probabilistic risk assessments were. Both of them were utter failures. So when people stopped doing it because they want to use them, they found the experts on the exact same system had 3 and 4 orders of magnitude difference in their risk assessment. I mean, that's crazy. I just got involved in a large defense program in the UK. They wanted me to come because the company was fighting the Ministry of Defense, the government, because the government wanted to use probabilistic risk assessment. The probabilistic risk assessment for this system, I can't say what it is, but for this system was at 10 to the minus 12. I mean, it turns out there shouldn't be an accident for 500,000 years. In the first year, this system crashed 5 times. I mean, so the government likes it because what they tell me, I talk to them. I say, well, why do you use this? And people say, well, you know, these systems are so complex, we can't understand them. So we want a number that we can make a decision on. But the number is bogus. The number is meaningless. So you're making a bad decision. You'd be better off coming up with other methods, and there are other ways of dealing with these complex systems than using phony numbers. We actually have had the industry, the companies, and the engineers are now arguing they want to use Sdpa, our analysis method, and to certify their system. And they've been arguing with the government in the U.S. and well, this example in the UK, and they're going to the regulators and saying we don't want to use PRAs, it's not working for us, and we want to certify it based on Sdpa. And lots of standards now are being created to do this. Governments are, and government agencies are starting to listen to this and to change. But it's a hard argument because it's easy for them to do it badly.
Thank you, Nancy. What's your opinion about this, Chris? I would like in you, Eli. So what do you think about probabilities in the context of safety? I mean,
Are you asking me? Or?
To what extent are useful, in essence? So this is an interesting conversation.
I think
I'd like to hear your opinion.
What was going through my mind? Yeah, what was going through my mind? I think I agree. It's very dangerous to ever disagree with Nancy, I've discovered. But I'll say a few things, right? One thing is that where you have statistical data, absolutely you need the probabilities there. So for example, this morning, Johnson & Johnson announcing the number of hematomas associated with their trials of the vaccine. If you don't look at the statistics, if you don't understand that that's 8 cases in 40 million or so, then you misjudge the extent of the risk. And it's really important that people then have a point of comparison between that actual risk and the chances of a hematoma from COVID. And that's, you know, that's based on data, but it's not looking at the kind of Bayesian use of risk and probabilistic assessment, which are based more on belief about the engineering of an artifact. So you know, there is this traditional distinction between frequentist statistics and Bayesian statistics. And I'm a frequentist because I can use the data and I can question whether or not the data is reliable based on things like underreporting, but there's a basis for that. But when it comes to Bayesian statistics, where you're really making judgments about future performance based on an uncertain environment, then I think we have a much more interesting.
I have nothing against statistics if you're really looking at statistics, but what happens in these systems is they can't get probabilities for software, so they ignore it. They assume humans operate randomly and make errors randomly. They don't. So you assume away. All you can look at is a little tiny piece of the hardware of the system and say this is the risk. I mean, that's crazy. You're not getting anything that's useful. There's a program in the United States, SubSafe, which is our nuclear submarine program, the most successful safety program in the history of the world. They have not had an accident now for 57 years. And they forbid the use of probabilistic risk assessment. They say you can use quantitative numbers. They're not against quantitative numbers, but they say they have to be verifiable. There has to be some way to verify that those numbers are correct. And they call it objective quantitative evidence. We've got to stop playing this game and pretending that we're doing something and ignoring the fact that it's not working. It doesn't work. It hasn't worked. Every accident has a PRA that says it wasn't going to happen, usually in exactly the way it happened.
Okay,
So,
Nancy. Okay.
I have no opinion about this whatsoever.
Okay, no probabilities for safety. Take the message, people. So a few words from you, Eli, and we need to close. We have a few minutes. Please, Eli, your thoughts on the use of probabilities, if you can. Or
probabilities, I agree. I mean, in safety, as I said, it's a zero tolerance. I mean, probabilities have to be executed based on engineering studies and lessons learned. Each activity has to be subject to a risk assessment. This is how we operate, where the risks are calculated very concisely. I might agree and disagree with the issues of probabilities. The use of probabilities can be used into further development of risk management and risk approaches, especially those related to automated systems and intelligence. Again, zero tolerance to risks and to HSE is a strategy that we've been living into it. It might be old-fashioned as a name. However, I guarantee, Professor Nancy, that it is in line with your thoughts and ideology.
Okay.
Thank you. It was a pleasure talking to all of you. Thank you very much.
all right, I truly enjoyed our session. Chris Johnson, thank you very much for being with us. It was a great honor, and it was great seeing you again after all these years. Eli, thank you very much for stepping up and do your presentation and contributing to this session. And Nancy, thank you very much for your time. I know you are quite busy, as Chris, as Eli. I know everybody's busy. Thank you for your time, and we will talk later on in the roundtable. So thank you very much, everybody, and thanks everybody for watching. Bye now.